9:30. So, so thank you all for coming today. So very good morning to all of you. So today what we're going to do is yesterday we talked about stability analysis. We also looked into aspects of lubrication theory and all that, lubrication approximation. Now, the thing is we want to see the applications of these. And the first example I would like to talk about is about multi-component evaporating pools. I mean, one of the things I would like to clarify here is that when you say multi-component, this is usually in the working I'm going to show you, this is a binary component mixture. Okay. Now, if this is a binary component mixture, you will have two components, two active components A and B. Both of them can be volatile. Okay. So there is no restriction on which one is more evaporating than the other. Okay. You can have a competition. And obviously, it's an evaporating and it's a pool. So the first case we'll consider is a pool because one of the advantages of a pool is that it has no contact line. So at least one thing we don't have to worry about is the contact line. But we're going to do the drops as well. I'm going to come to that probably tomorrow. Okay. So two key things we are taking into account is a binary component mixture, which is evaporating and in a pool. So that means there is no contact line. Okay. And typically, why do you need to study this? So for example, if you want to have a electronic circuit and you want to pattern the surface. So normally you can, one way to do it is evaporate the surface and so that you can have patterns. Okay. So that the deposit is having certain pattern, then you can do that. And it's a very important thing because most of the liquids that is used or most of the coolants that are used there are multi-components. So typically, if you consider just a coolant system, okay, this is just an example of a coolant system. So you can see that it's a, if you look at it, there's no interface, so it looks homogeneous. It's a miscible mixture. You usually have some glycol, you will have some other, all kinds of nonsense. You'll have all kinds of additives. You'll have water, of course. So you can see that it's a pretty complex mixture. Okay, and one of the things when I was working in Hindustan Lever, one of the things we always dealt with is when you have a miscible mixture with many components, and each one will have their own thermodynamics. Each one will behave with another component in a completely different way. So if you have 10 components, you can have 10 number of ways of interactions. So it becomes a very complex thing. And in Unilever, what we used to do is when we form a liquid detergent, okay, from in the shop shelf, you will see that it looks of the same color. There's no phase. If there is phase separation, no one will buy it. Okay, but all of these things are susceptible to phase separation because if you change the conditions of temperature or pressure, they might just simply separate off. So what in Unilever we do is we look at these things we put under temperature controlled environments. We look at very high humidity, we look at very less humidity because we want to check the shelf life of this. And there was one incident where we were making a liquid detergent. So we had, instead of glycol, you will have a detergent. You will have all kinds of stabilizers there. You will have color because people like to have color in their detergent. You will also have some of the perfume or some kind of a essence because people like to have that, otherwise they will not buy it. Okay? And so we developed one detergent for the South American market and we were testing it. First month it was looking perfectly fine. 2 months down the line, we could see some discoloration. Okay? And then the problem starts. The problem is what is causing the discoloration? You've got 10 components there. Any one can be a culprit. Which one is the one which is causing this? Over several trial and error methods, we found that it was the essence, it was the perfume that we added that resulted in discoloration and phase separation. Okay, so we had to change the perfume. So you almost have a finished product, but then you're thrown back into the drawing board because it's not durable over a period of time. Of course, if we just left it for a month and we thought that it's going to live forever, we were mistaken. It didn't. It has its own thermodynamics, it has its own kinetics. So slowly it started acting on it. Yeah. So one thing you need to be very careful about is when you have a liquid mixture, we have to be very worried about their properties. And the thing is, the mixture thermodynamics. So typically, I know that in basic thermodynamics, we don't account for mixture thermodynamics because it's a bit complex. In Chem-Eng, we have in third year, typically we do chemical engineering thermodynamics, where we introduce bits of mixture thermodynamics. But again, that's also at a very basic level. So when we design such systems, we need to really look into things very carefully. So one of the important things that people are looking into is bespoke liquid design. Okay, so if you want to design a coolant, which will work at microgravity, that will be completely different than a coolant which is working for your heating systems here. Okay, because they have completely different needs. Okay, so coolant design is an important aspect, and therefore multi-component systems are looked at it have to be very carefully looked at. So what we're going to do today, as I mentioned, is we're going to take a simpler problem. I wouldn't say simpler. I would say we'll reduce one complexity. We'll not have a contact line. Okay, so the problem we are looking at is basically a pool. Okay, so this pool of liquid is sitting on a solid, and this solid is heated. Okay. This solid is heated and it's at a constant temperature Tw. This is a liquid mixture. It has A and B. Both A and B can be evaporating. So Ja is basically the mass flux, and you can also have J is equal to J plus Ja plus Jb. Okay. So both of these guys can evaporate. Okay. Typically, it's the most volatile component which evaporates first, but that doesn't mean that the other component doesn't evaporate. Obviously, the evaporation depends upon this interface temperature. So there is some T, and T is a function of both space as well as time. Okay, space as well as time. And one of the things you can imagine is these are very thin liquid films. And the example I'm looking at is a water ethanol film, which is about 1 micron thick, or around a micron thick. Okay, so these are very thin liquid films, and you are evaporating these things to develop a pattern. Okay, so here one of the quick things we can look at is if we say that the initial film thickness is around h0, okay, and the length of the film is L0, and here this is a very thin film over a very large surface. It could be on a chip or it could be on your silicon wafer. Okay, so then we can put a lubrication parameter epsilon, which is the ratio between the height and the length of the film, which is very small. Okay, and that really will help us, because just as we did yesterday, if you have a lubrication parameter, if you have a system which is of which one side is much longer than the other, then you will have a reduced level of equations to worry about. Okay, so we're going to look at that. So we have certain, we also assume some sort of a velocity scale. So this is based on this. We have one thing we assume is rho A is equal to rho B. So typically, if it is water ethanol, both of them are nearly the same density. Okay, they're not, but we can assume that for these purposes, they are the same density. Viscosities are different. Okay, viscosities and everything else is different. And what we do is then develop scaling. So the first important thing we do is we scale with respect to component A, which is probably the more volatile component. Okay, so you can have your own scaling. You can develop your scaling in any way. So first thing you will see is that you will have some kind of a Prandtl number, which is Cp mu by kappa. Okay, Cp mu by k. You will also have a Peclet number. So you have thermal conductivity. You will also have thermal diffusivity playing a role because it's an evaporation problem. Plus, because it's a binary liquid, there is mixing happening in this, mixing of components happening within this. So therefore, that has to be accounted for. So you've got the diffusivity. You obviously have a capillary number because there's surface tension on the interface. And this surface tension is not only a function of temperature, so therefore you have a thermal Marangoni, but your surface tension is also a function of concentration. So you'll have a solutal Marangoni. Okay, so you'll have both these components there, thermal and solutal, and obviously what you will have is some sort of a evaporation number. This is the ratio of this is latent heat, okay, and this is sensible heat. So we define the ratio of sensible heat to latent heat as some sort of an evaporation number. And very importantly, this is from molecular kinetics theory. This is the Hertz-Knudsen equation. Now, if you look at Hertz-Knudsen equation, it tells you some it gives you first principle assumption on the rate of evaporation. Okay? And that rate of evaporation is dependent upon a parameter, what we call as an non-equilibrium parameter. Okay? I'm going to show you how this comes into picture. Okay? So you can see that you will have a latent heat of the system. You also have a latent heat ratio because you've got two components, B and A. So you'll have a ratio between the latent heats. You will also have, so if you look at the Hertz-Knudsen equation, this M is basically the molecular weight of A and molecular weight of B. So you also have a molar ratio, okay, of B versus A. You also have vapor pressure because if A is more volatile, PA, that is vapor pressure of A, is more pronounced than vapor pressure of B. So you also have a competition at the vapor pressure ratio. You have the density ratio, competition between densities. Of course, in this case, because rho A is equal to rho B, this is competition between liquid and vapor. So it's nothing to do. But then you also have surface tension ratio, because if it was pure A and if it was pure B, each one would exhibit completely different surface tension. You have the temperature coefficient of Marangoni, and I guess the next one is, yeah, temperature coefficient of Marangoni. So basically you will have Marangoni coefficient for not only A, but also Marangoni coefficient for B. So you'll have a Marangoni ratio there as well. So you can see, just by adding one more component, you have a very, very complex problem. Okay? This is supposedly a simpler problem comparison to a droplet, but just look at the level of parameters you have. It's really mind-boggling. Okay? So what we have to do is we have to look at, obviously, one can make assumptions. One can make assumptions that, okay, this is bigger than this, so I'm going to get rid of that. But at the moment, I have no idea, because it's a very general formulation. I have no idea is which one can be ignored. So I'm going to look at everything, but then I can cut down things once I have the full equations. So this is the typical non-dimensional governing equations. So you can see that you have the mass balance, you have the momentum, just as we did yesterday. You had the momentum in the x direction, and in my derivation yesterday, I think the vertical direction was y, but here it is z, doesn't matter. So you got the momentum equation is z, and you can notice that I have not done anything with gravity. Okay, I have not done anything with gravity because this is such a thin film, I'm not really bothered much about it. In fact, this is not completely correct. Okay, when you have evaporation, you will have buoyancy effects come into picture. Okay, I'm ignoring those effects. Okay, I'm ignoring those effects. Now, if I look at the energy equation, you got the temperature, you got the usual energy equation here. You can see, you will see that lambda is the thermal conductivity and things like that, so you'll have the effect of that. You also have the concentration equation. Now, the concentration equation, this is, I have done some tricks here. So one of the trick I have assumed is this is only the liquid phase concentration equation. Okay, so this is the concentration equation in the liquid phase. My objective is to identify concentration profile on the interface, okay, as it evaporates. I'm not considering the vapor. In the vapor, I'm assuming some things. I'm assuming that there is some kind of a concentration profile. I'm not simulating anything in the vapor because for me, the vapor is almost stationary. Okay, it's a quiescent atmosphere. So it's just like you have your silicon chip, you have deposited whatever you have to deposit there, and it's evaporating in a clean room where there is no convection. Okay, so I'm not bothered much about the vapor phase. Again, that is a severe assumption. Okay, so I'm not assuming any distribution of concentration in the vapor phase. In reality, it does affect, but I'm going to come to that later. Okay, so and then, of course, as I mentioned, you got lubrication approach. So we can say that the lubrication parameter epsilon is much less than 1, which means that the height of the interface is much less than the length of the safe. And if I put this, I'll reduce these equations like yesterday. Okay, I'll reduce these equations yesterday. In fact, I'll have terms like epsilon square sitting all over the place, and I can ignore many of these terms. Okay, I can say that because epsilon is much smaller than 1, epsilon squared or epsilon cubed is even smaller than 1. So all those terms I can ignore. Okay, if I ignore all these terms, I'll have a reduced set of equations. And what I can do is I'll have a reduced set of equations, and these reduced set of equations are basically concentration at the interface and the height of the interface. Okay? If I implement the boundary conditions as well, I'm just going to show you the boundary conditions. Hold on. So these are the boundary conditions. So you can see that this is Z is H equal to XT. So this is at the interface. Okay? This is at the interface. This is basically giving you the mass balance and the mass flux. Okay? And obviously, if something is evaporating, the level of the height would change. So that is the expression that looks into the, this is the expression, these two guys are actually looking into the height change as well as the mass change. Normal stress balance on the interface, you'll also have a tangential stress balance. So tangential stress balance, you will see that there is the effect of capillary number here. Okay, and also in case of a normal stress balance, you will have capillary number. You will also have the effect of solutal as well as thermal Marangoni. So whenever you see MT, that is thermal Marangoni, MC is the solutal Marangoni. Okay, and then obviously at the interface you will also have energy balance. So whatever energy is coming through has to go up. So this is the energy balance, and you can see that this is mass flux of A, this is mass flux of B, and this is basically the ratio of the thermal latent heats, ratio of the latent heats, and so on and so forth. So if you evaluate those things, you will get you will have an energy balance equation for the at the interface. This is the concentration profile as you have evaporation going on at the interface. So this is basically again concentration mass balance. Okay, just concentration mass balance. This is the evaporation rate, and this is the local Peclet number. So basically what it says is, if I'm delivering this much amount of material here, that much amount of material is getting evaporated. That's about it, nothing else. Okay, and of course kinematic is basically showing the level of the interface, and these are the crucial ones, the evaporation fluxes. You can see that you got evaporation flux of A and evaporation flux of B. They are slightly different than each other. They can become equal, but I'm making sure that they're different. Okay, and there is this equilibrium, so-called equilibrium parameter K. I'm going to come to that soon. And obviously, your surface tension is a function of both concentration as well as temperature. Okay, so you can quickly see that it becomes a, so when you employ all this, and of course, one of the other boundary condition is at Z equal to 0. At Z equal to 0, it's very simple. It's a wall. And you've got a wall, you've got a fixed temperature T1, T equal to 1 or T equal to whatever T heat, whatever it is there, and then U and velocity are all 0 at the wall. So these are the two boundary conditions, and if you see this, these boundary conditions with respect to these set of equations, what you will have is you will evolve C as a function of T and obviously space, okay? You will also get H as a function of T and space. So you'll get these two relations. If you just substitute all of these things, I'm not going to go through all of that, but you'll get these two equations, and they look terrible. Okay, they look really horrible actually. And the parameters that we use is water ethanol system, and as I mentioned, we are looking for the case where you've got a very thin film of water ethanol system. Okay. Very thin film, and these are the properties of water ethanol system at that particular height. Okay, is there anything else that I've missed? Probably not. Okay, now as I mentioned, you will get H as a function of T, and because it's a very rich problem, you will have all these terms. And the thing is, what I've done is I've not ignored any term. Some of these terms will die anyway. We are not really bothered about them. But what is more important is what each of these terms is contributing. So now if you look at H versus T, this is the variation of interface with respect to time. So you will see the evolution of interface and evolution of interface with space, because there is also an X and with respect to time. Okay, so if you see this, you will find that you got several terms which are important. Wherever you find an E, that is the evaporation term. Okay, this is the evaporation, this is the effect of evaporation. MT and MC look at solutal Marangoni, the strength of solutal Marangoni. So what you can do is you can actually cancel these terms. So if you know that, okay, the thermal Marangoni is pretty small for your system, this term will go away. Okay, the effect of this term is small, and so on. So you can make those decisions. Of course, one of the things is surface tension. This is a crucial role. And there is another term which I have put here is the disjoining pressure. And there is a reason for that. Now, whenever you have a very thin film, I've just exaggerated this, and you've got this height of the interface which looks like that. It is forming these waves, and sometimes the height of the interface almost goes very close to the wall. Okay? So whenever it is almost tending to close to the wall, continuum approximation breaks down. If there is a kind of a puddle, if there is kind of a, if it's forming a kind of a contact line, if it's touching the surface, it's breaking the continuity of the equation there. Okay? That breaks down. So to avoid that, what I do is I put some kind of a disjoining pressure. So what does that disjoining pressure do is, okay, it can go as small as possible, but it is having some sort of a tolerance, and that is determined by the Hamaker constant. Okay? This is the point where it forms some kind of a precursor film. Okay, this is the point where it, so this is also a modeling device to stop the simulation from going mad, but again, this is a, this also prevents, it also shows some level of dry out. So we can say that the moment your height of the film becomes close to the Hamaker constant or becomes close to the disjoining pressure equation here, that is when you almost will have dry out. Okay, it's not fully dry out, but because there is a film, but then this is a device to control that. And you, as you would know, Hamaker constant is completely dependent upon the van der Waals, and that is dependent upon the material properties and so on and so forth. So okay, so you got this disjoining pressure to help make sure that you don't go for a complete dry out and you don't come for a, you don't break down these equations completely. Okay, and of course, and there is this another set of equations which is basically on the vapor recoil. This is basically the effect of vapor on top of the interface. Okay, so this is effectively, we are not solving for anything in the vapor phase, but what we are doing is we are approximating it. Okay, so this is accounting for vapor recoil at that point. The other thing is, obviously, similarly as I mentioned, you will also have a concentration equation. Okay, again, concentration equation is a function of time with respect to the height. So basically, this is the concentration equation on the interface. So when you say H, H is basically the height of the interface or the shape of the interface. C is the concentration of the interface, concentration on the interface. And here you will also see very similar kind of very similar set of equations, very similar set of parameters. And you will see, I mean, it is heartening to see that both of these equations have accounted for most of the forces that is involved. So you will have the effect of concentration because of thermal Marangoni, effect of concentration because of solitary Marangoni. Obviously, this plays more role than that in case of concentration. You will also have diffusion equation, diffusion within the liquid phase. So how fast, if your liquid mixture has got a liquid phase mass transfer resistance, this will have a more resistance here. Okay, this will have more resistance. This is the evaporation number. So basically, if you have more evaporation, you may actually flood the interface with more volatile component quickly. Okay, so there are various ways in which these terms can act. Again, similarly, you'll have effective surface tension and disjoining pressure, and then you've got the vapor recoil. So the most important parameters here in the system is solitary thermal and the disjoining pressure actually. So the thing is, so what we have done is, if I stop my lecture here, and if we solve these equations, if we actually plot these equations, what you will get is, you will see, I'm going to show you the videos later. What you will see is you will have initially a flat film. This will suddenly develop into kind of a wave, and basically you will see how it evolves and how it evaporates with time. Okay, that is H. And similarly, what it will show is concentration, how it is changing with time. Okay, if I just plot those things. Okay, now what we're going to do is basically, we want to understand what causes. So basically, if you know, for etching and for developing patterns on surfaces, there are instabilities that can trigger that. So what we're going to do is, like yesterday we mentioned that whenever you have some sort of a base state, you put a kind of a small perturbation and then you let it evolve. So we're going to do the same thing here. So here again, what we are going to do is, this is an unsteady system. So you've got evaporation going on. You start from a flat interface and then at a later stage, this flat interface becomes even thinner. Okay? So typically what we're going to do is we make an assumption. The assumption is that the time scale of evaporation is so big, it's so slow evaporation, that it allows for instabilities to develop. Okay? So which means that I can freeze the simulation in time, and then for each of these time steps, I can actually calculate it, do a linear stability analysis. This is called as a quasi-steady stability analysis. Okay? The advantage of this is that at every stage of evaporation, you will see how the system behaves. Okay? And this is for very slow evaporating systems. Okay? Okay? So this is basically some sort of a perturbation that we give. So we give a perturbation, and because we are looking at h over t, we have equations with ht and ct. So we're just going to give perturbations in h and c. I'm not worried about the velocities. I'm not worried about the pressure or anything like that. I'm just focused on the height of the interface and the concentration on top of the interface. Okay? So I can give these perturbations and let it evolve. Okay? So, and basically what I'm doing is I'm freezing my base state, freezing my situation and time, and then putting these perturbations at every phase state. Any questions so far before I go ahead? Okay, so one of the things that you would see here is you've got ikx, you've got an ikx here, okay. Typically, k is the wave number. So what is a wave number? So and k is usually complex as well. So k is complex, which means that this is something like a real part and an imaginary part, okay. So if I evaluate e to the power I kx, this is e to the power I kr plus I ki x. So if I do this, this becomes e to the power I kr minus ki x. Okay, so this is the imaginary, the real part of the wave number is sitting into the imaginary term, and the imaginary part of the wave number is actually causing the growth rate with space. So if you split this up, it is e to the power I kr divided by or multiplied by e to the power minus ki x. So you can say that this is contributing to the growth in space, and this is basically contributing to the frequency. Okay, so that's how we actually look at the stability analysis, and it's very, very useful to have that perspective in mind. Okay, now what we're going to do is we're going to do that, and it looks, again, I'm not going to go through it, otherwise I'll spend 3 days doing all this. So I've just substituted, what I'm going to do is I've just substituted h as a function of a base state which is based on certain situation in time with respect to, and some kind of a perturbation ht. And this, the magnitude of this perturbation is very small. Okay, so you can imagine you already have a film of a micron, and on top of it, you're putting a very small submicron perturbation. So typically at the level of nano. Okay, a very small perturbation, and people can ask me, where will these perturbations come from? They come from everywhere. So whenever you do an experiment, you can have a disturbance of any kind. Okay, they can be small, they can be big. It could be temperature driven, it could be acoustic driven, it could be anything. Okay, so once you evolve this, you will get an evolution. This is the stability equation for the interface, and you will similarly get a stability equation for concentration as well. Okay, now what we're going to do is we're going to look at, the idea is, as I mentioned, the stability analysis. So you already have answers of how your interface structure develops with time. You did that lubrication. But what will this give you is, at what point will it get unstable? Okay, now if you look at it, if you look at this, you can say that you got, as I mentioned, you've got ikx there. This is the growth rate in space. Okay. What we can do is we can put a frozen interface. This is a growth rate in time. Okay, we can assume that the interface evolves with time with a certain growth rate. Okay, so height of the interface with time is initial height at 0, e to the power r tau. Okay, similarly, concentration evolves with time as well. So you'll have evolution with space as well as evolution with time. Okay? And R is the growth rate in space. Okay? And the idea is we want to understand what is R. Okay? We want to know what is R. And if you do the whole stability analysis, we get this weird equation looking here. And I would say all of these things, you have the Hamaker constant, you will see the effect of solutal Marangoni, etc. All of these things come into picture here. But the most important term I would ask you to look at is this particular term. This is half. In fact, the determinant D also has solutal and thermal Marangoni. The sign of the determinant describes the nature of the instability. If the determinant is positive, you have got the growth rate which is more real. Okay? But if your determinant is negative, you have a real part for the growth rate as well as an imaginary part for the growth rate. And that instability is very different than which is a real one. Okay? And we have noticed that in our simulations and also in experiments. Okay? So what we can do is we can set, so if you remember, we had a case, we assumed that there is an equilibrium constant called as K, and when we set K equal to 0, it actually is a fake case where we say that the temperature across the interface is constant and it is equal to the bulk of the liquid. So essentially, you have very slow evaporation, but that is a very special case. Technically, we never have quasi-equilibrium. So even if we do such kind of a fake case, you will see that when you suppress evaporation, so when E equal to 0, everything is stable, obviously. If there is no evaporation, there is nothing happening. So at least this simulation shows that all the growth rates are negative, there is nothing which is happening. Great. But then if I introduce some sort of evaporation, this is a very small evaporation there, what you will find is that there would be some parts of the growth which is unstable, some parts of the wave numbers which are unstable, and the other ones are completely stable. Okay? This is the region, this oscillatory instability. We call it as oscillatory because the simulations show oscillation, so that's, I'm going to come to that. But this is where this happens when your determinant is negative. Okay, you have both the imaginary and the way these two behave is completely different. And the patterns they leave behind is also very different. This is the real case where you have non-equilibrium. This is the typical growth rate. Again, you have this determinant sitting there, which is the square root of determinant. So if you have a positive determinant, it's a real. If it's a negative one, you'll have both the real and the imaginary one. Okay, so this is the first case where the determinant is completely real. This is the evaporation is completely suppressed. And when you have a non-equilibrium case is when both these components are having very different properties. One wants to be volatile, but of course you have suppressed evaporation. The other one is less volatile, so there is a lot of mixing going on. There's a lot of mixing and convection going on. So this is where you will have some sort of an unstable mode, which is a smaller one. But again, evaporation, you're trying to suppress evaporation. So you're making sure that there's absolutely no evaporation. But then this is the real case where you have evaporation. So you can see that there's a huge range of instability. There's a huge range of wavelengths where things are unstable. And there is obviously a small region where things are stable. But you can see that whenever K is small, the way K is related, K is inverse of the wave number. So the wave number is inverse of the wavelength. So whenever K is small, so wavelengths are high. Okay? So if K is small, that means it's a long wave. Okay? That's why we call it as a long wave instability. And whenever lambda drops, your K is very high. So at high wave numbers, you have very tiny wavelengths. Okay? So what we can do is we look at these instabilities very carefully. Okay? So this is the monotonic instability when the determinant was positive. Okay? So when the determinant was positive, this was a case where you've got obviously you've got the pool of liquid. In these cases, both the solutal as well as thermal Marangoni are collaborating with each other. They are in the same direction. They are pulling, so you can see that everything is pulled away from the crest. Okay? So in this case, the B is less volatile than A, which means that as A evaporates, you've got a dip, and you can see that the concentration has depleted. This is C minus. Because there is a dip, your temperature is closer to the wall, so this is a higher temperature. The temperature at the crest is less, so therefore there is this thermal Marangoni which is pulled there. The concentrate, because evaporation is, this is a lower concentration region because it is close to the surface. This is a higher concentration region, so there is a pull in both sides. So essentially, you're having a pull on both sides in the same way. So essentially, this will develop into a kind of a puddle. Okay, you will find, so either if you have a system which is representing of that, you put your film there, you will form these big regions of puddles. You can have puddles in this way, and it's a completely depleted zone in the other way. Okay, or the other way around as well. So basically, this is the region where you have monotonic instability. The other one is a more complex one. So in this case, you can imagine you have again a wave close to the solid. So the temperature, because it's close to the solid, the temperature is higher in the crest than on, in the trough than on the crest. So T plus and T minus are in the same direction as before. So you've got the thermal Marangoni which is pulled in that way. But in this case, your B is more volatile than A. That means that you've got A's, the concentration of A is richer in this region than concentration of A there. So that means that the solitary Marangoni is going in the other way. Okay, so you've got this push-pull system here, and whenever you have a push-pull system here, you will have quite a complex dynamics. So this is when the determinant was actually negative. That's when you have an oscillatory instability. Okay, now if you look at it, so what we have, I'm going to show you the simulations on how actually and practically it looks like. So what we have is here, we have the ratio between concentration solitary Marangoni versus thermal Marangoni. And this is basically, I think, the ratio between relative volatilities. So what we have done is we have actually plotted these quadrants, and we have determined which one is a quadrant which will give you oscillatory instability or a monotonic instability. So if your system is in this region, you can imagine that you will only form puddles. So if you want to have a surface which has these blobs of etching there, that is the region where you want to look at. But if you want to have a more complex pattern, then this is where your red dots are. So that is where you have the oscillatory instability, and you'll form a more complex pattern there. Okay, so this is a different evaporation. So this is a higher evaporation rates, and this is at a lower evaporation rate. But you can see largely, you can see that as you increase evaporation, you got more of oscillatory instabilities in these quadrants than the others. So how does it actually look like? So this is basically, I don't know, this is the concentration. I don't know why the line is being, anyway. And that is temperature. You can see that in this case, all of these are acting on the same line. So basically, if you look at this, H is basically your pink line here. You can see that it has formed a puddle on this side. It's almost going to zero in the center, and again forms a puddle. So you can imagine that it's basically a very concentric, not a concentric, but you can form concentric circles from here. Okay, so this is what your monotonic instability looks like, and we have seen that in experiment as well. Okay, so this is how the simulation evolves with time. So this is just the same representation in another way. This one is the case where you have an oscillatory instability. So here, solitary and thermal Marangoni compete with each other. So obviously you've got this push-pull system, thermal Marangoni doing something different, completely opposite to what the solitary Marangoni wants. So and what you will have is, you'll have a very rich interaction between the two, and you will form different types of waves, and you will form different types of, again, it depends upon your initial conditions completely. So there's nothing which we can't really predict what will happen. So it becomes a kind of a very, very rich system here. Okay, so this is what your evolution, this is obviously when you go into non-linear regime, it becomes even more complex. But you can clearly see that when you have this push and pull mechanism and oscillatory instability, you can get to much more richer patterns. So you can essentially see, if you want to have a complex pattern, you probably want to have something like an oscillatory instability on your system. What we also do is, because what I'm doing here is basically capturing the height of the interface or the height of the amplitudes with respect to time. So basically what I do is I look at one wave. So I start from a simple wave, okay? So this is my primary mode, and I look at the amplitude and how it grows, okay? So at some point it might grow in this way, okay? So this is how your growth rate is. What I do is I then take the other harmonics. So basically I take a Fourier transform and find out what are the lower order harmonics. So here I'm looking at the height of the interface. So this is h. I'm looking at the temperature at the interface. So you can see that all of these temperatures also grow in the same fashion, okay? So the growth rate of the interface and the growth rate of the temperature is almost the same. You can also see the concentration effect. You can also see how the concentration changes with time, okay? But then what I want to check is how are the lower order magnitudes, because once you become nonlinear, you have lower order, you have higher order harmonics coming into picture, okay? So here what we do is we take this, we take the ratios between the slopes of each of these things, and we find that basically it's the solutal Marangoni which is actually driving the whole instability. That is the strongest. If you look at this, if you look at the system, if you didn't have a second component, you would not have many of these physics coming into picture, okay? So concentration plays a huge role in terms of determining the evaporation characteristics of a multi-component system, okay? In this case, we made the system supposedly simple by not having a contact line, okay? But then still you can see how strong, how rich the system becomes just by adding one more component. You can imagine that if you have more and more components, it becomes more and more difficult, okay? You will have things like spinal decomposition, you will have Oswald ripening, you will have all kinds of other things. And that is something which we look at very carefully as well, okay? But we are still doing it. There's a lot of work being done, especially when you have a ternary mixture or a quaternary mixture and things like that, okay? So this is some reading I would like you to do. So all of the work which I've shown has been published here, so you can have a look. But I would like to open the floor for questions or anything and discussion, because I'm done with the lecture.
Maybe first one, you mentioned that we can take system state at different time steps.
Yeah.
And then we do the stability analysis.
Yeah.
So how we can decide the time instance?
Very good question. Very, very good question. So the way we do it is based on my time scales, ratio of time scales. So the main assumption I have made here is that evaporation is very slow. So if the evaporation is very slow, I can freeze my base state with time in the initial stages. But definitely what I do is I look at this, I look at the picture of the interface. If the interface becomes non-sinusoidal, I'll not take those. As long as the interface is sinusoidal, I'll only take those snapshots.
And is there any critical amplitude of the sinusoidal?
Yes, there is. I think it is. I think it is. From what I remember, I think it's about 10% of the interface thickness. Yeah.
And in terms of this oscillatory instability, because thermal Marangoni and concentration Marangoni are in the opposite directions.
Yeah.
But still, we have the ratio of thermal Marangoni and the concentration Marangoni.
Yeah.
So, can that ratio somehow govern whether the film will be breaking or it will be?
Yes, it does. You're absolutely right. So basically, if you look at the plot here, sorry. So if you look at the plot here, the thing is, the moment you change your ratio between concentration as well as temperature Marangoni, you can go from one state to the other. Oh, condensation. Very good question. We have not done that. We have not done that. One quick answer would be that If I assume that the direction of evaporation is almost opposite to condensation, then we may not be very far off from what we are here. But condensation is a slightly different phenomena, and that's an ongoing thing. Yeah. Any further questions? Do you guys work on mixtures here? Yeah. Yeah, it's quite it's quite of a nightmare. Yes. I mean, we know that there are several people who have attempted numerical simulations. I mean, Debrishi is doing that now in a what we think is a much more proper way. But let's see.
So I think in simulations you might be handling the contact line as well.
Yes, we handle the contact line and the simulations, and there are